Hello and welcome to our lecture on the topic called implicit differentiation. Up to now we've seen many differentiation rules, and I hope you're comfortable with applying these rules in finding derivatives. Last time in particular we saw the chain rule, and today the topic of implicit differentiation is very similar to the chain rule. This will be our final technique for finding derivatives. After today's lecture, we'll be able pretty much to find the derivative of anything. It'll be a nice conclusion, I think. You'll be very confident that if you're given a function, you can find its derivative. We'll also do a different topic today related to implicit differentiation and the chain rule, and that's called related rates. Issues like this. If the radius of a circle is increasing at a certain rate, how fast is the area increasing? And this kind of idea applies to many topics, and we'll see this as the second half of the lecture. So I'd like to first step back to a problem I looked at last time, which was considering the circle x squared plus y squared equals 25, and how to find the derivative at any point on that circle. And in particular, let's pick the point 3, 4, which is on the upper semicircle. Last time what we did, you'll remember, is we solved x squared plus y squared equals 25 for y. So y turned out to be the square root of 25 minus x squared, and that is the formula for the upper semicircle. And then we took its derivative by the chain rule, and we obtained 1/2 25 minus x squared to the minus 1/2 times the inside derivative minus 2x, which simplified to minus x over square root 25 minus x squared. At the point 3, 4, that derivative equals minus 3, that's the numerator, over 25 minus 3 squared, all square rooted, and that's minus 3/4. So the curve has a negative slope there. The trouble with this technique, of course, is it won't work if y is negative, because we were only dealing with the upper semicircle. Well, today's technique will take care of that. Here's a picture of our semicircle again, and you see that at the point 3, 4, the slope is indeed negative. The tangent line is decreasing at that point. Well, here's the idea of implicit differentiation. You know how to find the derivative of a function that's written explicitly, like y equals f of x, like y equals tangent x, y equals x cubed. Those are explicit functions. But the equation we had, x squared plus y squared equals 25, y is kind of embedded there. It's not y equals something, but it's embedded. We like to say that y is an implicit function of x. It's not written explicitly with y on one side and all the x's over here, but rather y and x are kind of embedded together. And it turns out we'll be able to find the derivative without actually solving for y. It's kind of amazing. Let's see how this is done by looking at some fairly simple examples of derivatives. Now, I want you to think about this in the following way. Think of x as being the independent variable as usual, but think of y as being a function of x. Y depends on x. So every time you differentiate y, you'll get y prime. Okay? So here we go. What's the derivative of x cubed? Well, that's easy. We know that. That's just 3x squared. But now what's the derivative of y cubed given that y is a function of x? Let's be careful now. This is a chain rule. It would be 3y squared times the derivative of y, because y is a function of x. So it's 3y squared dy dx, or y prime. Let's do another one. What's the derivative of x plus 3y? Well, it's the sum of the two derivatives. The first derivative, of course, would just be 1, the derivative of x. And what's the derivative of 3y? That would be 3y prime, or 3 times dy dx. So in general, when the x's are being differentiated, you do it as normal. But when you're differentiating things involving y, remember to multiply by dy dx, just like you multiply by the inside derivative with the chain rule. Here's a harder one. What's the derivative of xy squared? X times y squared. I hope you realize that's a product rule. Good. So it's the first times the derivative of the second plus the second times the derivative of the first. Here we go. It's x times the derivative of y squared plus y squared times the derivative of x. Well, what's the derivative of y squared? That's 2y times dy dx, or y prime. So our first term is x times 2y dy dx. And then we add that to the second term, which was y squared times the derivative of x. That's very easy. That's just 1. So our final answer, with some simplifications, is 2xy y prime plus y squared. Good. Let's go back now to our circle and show how this implicit differentiation will give us a new formula for the derivative that will work any place on the circle, not just the top half. So start with your equation, x squared plus y squared equals 25. And the way you do this is you differentiate both sides of that equation with respect to x. Well, I'll do the right-hand side first. What's the derivative of 25? 0. That was pretty easy. How about the left-hand side? What's the derivative of x squared? 2x. What's the derivative of y squared? Careful. It's 2y times y prime, or 2y dy dx. Now, I've got the derivative in an equation here. All I'm going to do is solve for dy dx. So in particular, I'll move the 2x to the other side, and I have 2y times dy dx equals minus 2x, and then divide by 2y. You can cancel those 2's, of course, and you get the final answer that the derivative dy dx is minus x over y. Now this is pretty amazing, I think. We have found the derivative of this circle at any point on the circle. How do you find the derivative? Well, let's do an example. What's the derivative at 3, 4? We did that earlier. You would plug in 3 for x and 4 for y, and you get minus 3/4, just like we had before. But now we can do it for other points. We can do it at 3 minus 4. In other words, now we're on the lower semicircle. And that would be the same idea. You would plug in and you get minus 3 over minus 4, which would be 3/4. Wow. How about if x is 0? What's the derivative when x is 0? Well, think about it. For the circle, when x is 0, you're at the top or at the bottom, and there the derivative is 0 because the tangent line is horizontal. What about if y is 0? Well, if y is 0, you're over at the left and right-hand edges of the circle, and the derivative doesn't exist there because when y is 0, your denominator is 0, and you can't divide by 0. So this formula is really great. You see the entire picture of the derivative at any point on this circle. So let's step back and kind of summarize how we use or how we do implicit differentiation. Here are some guidelines. You're given some equation involving x and y, and you want to find y prime without solving for y. Here's what you do. You differentiate both sides of the equation with respect to x. That's what I did with the circle. Then you move all the folks involving dy dx to the left-hand side and everybody else to the other side. And then you factor out dy dx and then solve for it so that dy dx equals something involving x and y. So it's pretty easy to do. Differentiate both sides and then solve for dy dx. Let's look at a more complicated example and see how these guidelines work. Let's find y prime if you're given the following equation involving y. X cubed plus xy equals 7 minus y squared. Now you might say, well, Professor, I probably could solve for y in that equation. It's a quadratic in y, maybe you could, but it would be messy. But I don't have to solve for y. I can take this equation and implicitly differentiate it and discover the derivative. It's amazing. You never have to solve for y, and yet you know the derivative everywhere. Watch how you do it. Differentiate both sides with x. Here we go. X cubed, its derivative is 3x squared. Xy is a product rule. So it's the first x times dy dx, that's the derivative of the second function, plus the second function y times the derivative of x, which of course is just 1. Now the right-hand side. The derivative of 7, of course, is 0, and the derivative of minus y squared is minus 2y times dy dx. Good. I've done the calculus step. Now we just have to solve for dy dx. So I move all the dy dx folks to the left, and I get x times dy dx plus 2y times dy dx, and I move everybody else to the other side, minus 3x squared minus y. And then I factor out dy dx, so it's dy dx times the quantity x plus 2y equals minus 3x squared minus y, and then divide by x plus 2y, and you get the final answer, dy dx equals minus 3x squared minus y divided by x plus 2y. You know, I really think this is kind of amazing. If you give me a point xy on that curve, I can now tell you what the derivative is by that formula. I just plug in the x and the y. And again, you could have done this by solving for y. You might have been able to. But if I had changed the problem and said, instead of say y squared over there on the right, I had put y to the 6th power, say, then you wouldn't have been able to solve for it. It would have been impossible to do except by implicit differentiation. Let's look at another example. This one's kind of neat in that it kind of looks funny initially. Suppose you have the equation sine y equals x. Now be careful. That's not the same as y equals sine x. This is backwards. This is sine y equals x. You might recognize this from your pre-calculus days, that this is the definition of the inverse sine function. Wow. We'll come to inverse functions much later in the course, but this is actually sort of a key idea of inverse functions. But let's ignore that for the moment. What I want to do is find y prime given that sine y equals x. So what do? I differentiate both sides with respect to x. Well, the right-hand side's trivial. The derivative of x is 1. What about the left-hand side? Well, the derivative of sine y would be cosine y times the inside derivative times dy dx. That's the chain rule. That's what implicit differentiation requires us to do. And then solve for dy dx, and you get 1 over cosine y. Good. Well, that's a nice formula for the derivative, but I can do even better. Assume for the moment that y is between minus pi over 2 and pi over 2. What that means is that the cosine of y is then positive. In other words, if y is between minus pi over 2 and pi over 2, then cosine will always be a positive number. And remember from our fundamental identity that sine squared plus cosine squared is 1? That means that cosine squared is 1 minus sine squared, and if I square root both sides, I get cosine is the square root of 1 minus sine squared. So that formula, cosine equals square root 1 minus sine squared, comes from the fundamental identity of trigonometry, and it's the positive square root because I've restricted y to be between minus pi over 2 and pi over 2. Now look, I know what sine y is. Sine y is x. Look back at the original equation. Sine y is x. So if I take my dy dx, it's 1 over cosine, which is 1 over the square root of 1 minus sine squared, which is the same as 1 over 1 minus x squared. Wow. I mean, this is kind of bizarre. We started off with a trigonometric equation, didn't we? Sine y equals x. There's some trig in there. But look at the derivative of that. The derivative doesn't have any trig in it. It's kind of amazing. The derivative is 1 over square root 1 minus x squared. Again, this will come up again much later in this course, but it's kind of interesting, I think, how the trig kind of gets flushed away or it disappears. Notice also the domain of this derivative is x between -1 and 1 because you're taking the square root of a number there. Okay, good. I hope we're comfortable now with implicit differentiation. Again, you'll have some practice problems in the workbook, but this is not a difficult topic as long as you remember to always sort of add on that dy dx, just like you did with the chain rule. So now I'd like to turn to another topic that is a very applied topic. It has lots of useful results in so-called real-life applications. These are called related rates problems. And let me try to explain what's involved here. Up to now, y's been a function of x. Well, now we're going to look at applications where x and y both depend on a third variable. In other words, x and y will both be functions of a third variable, which we're going to usually call t. Not always, but usually called t. So x depends on t and y depends on t. Think of t as being time. So as time moves on, x changes and y changes. And that's why it's so-called related rates. They each have rates of change. Here's an example that I alluded to last time. You might have a circle whose radius is changing with respect to time. So r depends on time. Well, the area will also change, won't it? As the radius increases, the area increases. So the two variables, r and a, radius and area, depend on a third variable, time. So, in fact, let's look even closer to this example and look at a specific problem. I think you'll like this problem. It's related to pizza. Okay, suppose you drop a pebble, plop, into a pond, calm pond, and it forms ripples, circular ripples that go out from where you drop the pebble. And suppose the radius of the outer ripple is increasing at a rate of 1 foot per second. So every second, that radius goes out 1 more foot. The way we could express that mathematically is dr dt, the rate of change of the radius with respect to time, is 1. Dr dt is 1. The radius is changing at the rate of 1 foot per second. Question: how fast is the area changing? What's the rate of change of the area? Is it constant? And specifically, let's be more specific. What's the rate of change of the area of the circle when, say, the radius is 4, and then we'll calculate it when it's 8? Let's solve this problem. Well, with related rates problems, you've got two quantities that are changing with respect to time. Those are the area A and the radius R. What you have to do here is find an equation that relates the radius to the area. That's why it's called related rates. Well, can you think of an equation that relates the radius of a circle to its area? Well, duh. How about A equals pi r squared? The area of a circle is pi r squared. So that's our formula relating A and R. And now I differentiate both sides of that equation with respect to that third variable, time. So the left-hand side will be dA dt, the rate of change of area with respect to time. That's what we're trying to find, by the way. And what about the right-hand side? Well, it's pi r squared, and the derivative is 2 pi r. Pi is just a constant, so it's 2 pi r times dr dt, right? It's that inside derivative. It's implicit differentiation. It's the chain rule. So it's 2 pi r dr dt, but dr dt was 1 in this problem. We said the radius was changing at the rate 1 foot per minute. So it's 2 pi r, 1 foot per second, I guess. So it's 2 pi r dr dt equals 2 pi r. So I now know how to answer the question. When r is 4, a prime is 8 pi. Just plug in 4 for r. So the rate is changing at the rate of, the area is changing at the rate of 8 pi square feet per second. And when r is, say, 8, the rate would be then 16 pi r. So it would be, excuse me, 16 pi, which is 16 pi square feet per second. Notice the following. As the radius increases, the rate of change of area is getting larger and larger. It goes from 8 pi to 16 pi. And I'd like to call that the pizza principle. You know, if you buy a pizza of a certain radius, say a radius 10 inches, you get so much pizza. But if you buy one of, say, 15 inches, you get a lot more area, don't you? Because that increase in the radius, that extra 5 inches of pizza in radius, gives you an enormous amount of pizza area, because the circle's pretty big by then. Okay, good. That was a nice exposure to a related rates problem. We'll look at a much more complicated one in a moment. But let me pause to say why these problems are thought of as being pretty hard. My students tell me, oh, professor, I hate related rates problems. They're so hard. Well, here's why they're hard, I think. In the first place, they're word problems. I think we struggle in general with word problems in mathematics. It's a lot easier just to deal with equations. But once you have a lot of words, you got to read it, you got to figure out what they're talking about, etc. Another reason related rates problems can be difficult is they involve a lot of pre-calculus geometry and formulas like similar triangles, area formulas, volume formulas, because you have to relate these quantities by some geometric formula. My suggestion on these problems is when you get one in front of you, don't panic. Read it carefully, draw a picture, label the drawing with the things that are changing, the variables that are changing with respect to time, and take your time in solving the problem. These can be difficult, but I think they're kind of fun too, because they're realistic. So, that said, let me show you a realistic problem. I've simplified some of the functions so we can actually solve the problem, but I think you'll see that this is a real-life situation. Here's the idea. You're watching a space shuttle take off, and its position function is going vertically off from the Earth, and its position function is s equals 50t squared. And you have a camera which is 2,000 feet away from where the shuttle is being launched. And as the shuttle is going up, you have a camera and you're following the space shuttle with your camera. And you want to know how fast the angle is changing of your camera so you can keep an eye on that shuttle as it's going up in the air. So that's our goal. We're going to find the rate of change of the angle of this space shuttle as it goes up in the air. Here's a picture of the situation. You see the space shuttle taking off from the Earth and going up vertically with position function s, and then the angle theta, the camera is 2,000 feet away, and that angle is changing with respect to time. And notice that we can do some calculations with this picture right away. For example, from the Pythagorean theorem, the hypotenuse of that right triangle is the square root of s squared plus 2,000 squared. We'll need that in a moment. Also, we're going to need the cosine of the angle theta, and that is equal, of course, to adjacent over hypotenuse, 2,000 divided by the square root of s squared plus 2,000 squared. Good, so let's keep this picture in mind. We'll come back to it a few times, and let's start solving our problem. We want to find the rate of change of the angle of elevation. We want to find d theta dt, and we're going to find it, say, 10 seconds after liftoff. So how fast is the camera moving 10 seconds after liftoff. Good. Remember that the position function is 50t squared, so I know the velocity of my space shuttle. It's ds dt, the derivative, which is 100t. And we're trying to find d theta dt when t is 10. By the way, before we go on, notice that when t is 10, s, the distance, the position function, would be 50 times 10 squared, or 5,000 feet up in the air. Good. Well, now we need to somehow relate the two things that are changing. S is changing with respect to time, and so is the angle theta. Can we think of a relationship between S and theta? Well, look at the picture. What do you think? The angle is changing and S is changing. Is there some relationship between those two variables? Well, how about the tangent function? What's the tangent of theta? It's S over 2000, opposite over adjacent. And that relates the two variables. So that's going to be our crucial step in this related rates problem. You find a relationship between the two variables that are changing with respect to time. So let's write down tangent theta equals S over 2000, and now we differentiate both sides implicitly with respect to t. What's the derivative of the tangent function? Secant squared theta times d theta dt. How about the right-hand side? What's the derivative of s? Well, that's just ds dt, all divided by 2000. Good. Then you have to get d theta dt all by itself on one side of the equation. Well, secant squared is 1 over cosine squared. So if I just pull it to the other side, it turns into d theta dt equals cosine squared times, of course, 1 over 2000. And then ds dt, we know what that is. That's 100t. We just calculated that previously. Well, we're going to have to know what cosine is, and you might remember I pointed it out a few minutes ago. Cosine from the picture is 2000 over the hypotenuse square root of s squared plus 2000 squared. So let's throw all these things now into our equation for d theta dt. I admit, this is getting pretty complicated. This is why applied math is so difficult. Real life problems are complicated. They have a lot of variables and a lot of big numbers sometimes. But let's throw it all in now, and we get d theta dt equals the cosine squared, so that's 2000 over square root s squared plus 2000 squared, times the 1 over 2000 times the 100t. Now, some nice simplifications occur here. In the numerator, we have a 2000 squared, and on the denominator, there's also a 2000 over there on the right, so one of those cancels. We also have that the s squared plus 2000 squared, all square rooted, is then squared. And the square of a square root, they cancel each other, and we're left in the denominator with just s squared plus 2000 squared. Okay, kind of rough going, but we now have a formula for the rate of change of the angle. d theta dt equals that monstrous thing there. Well, we wanted to find out what happened when t was 10. When t was 10, s was 5,000. Plug those numbers in, and you get 2,000 times 100 times 10 for t, divided by 5,000 squared plus 2,000 squared. Trust me, that simplifies to 2 over 29 radians per second. Trust me. You just have to simplify that. It's unpleasant arithmetic. And that's about 12.4 degrees per second. So that angle's moving pretty quickly. 12 degrees every second. It's going up pretty fast at that 10-second mark. Good. That was a hard problem. I hope you had to struggle a little bit with that. It's a non-trivial application of related rates. So I'd like to sort of summarize. We now know how to calculate all the derivatives that we'll ever come across. Anytime you're given a function, be it explicitly or implicitly, you're now able to calculate its derivatives. By the way, calculators, good calculators, have these built in. So you can always check your work with your calculator. I invite you to practice calculating derivatives. We have a lot of problems in the workbook that'll get you sort of very comfortable with the skills we've developed these last few lectures. And now we're going to turn in the next set of lectures to applications of derivatives. We're going to use derivatives to help us graph and to solve so-called optimization problems, finding maximum values or minimum values. This will be very important in applied math, so I look forward to seeing you next time. Thank you.